wait a couple seconds. Let's wait a couple seconds. Yeah. I need to publish a direct link to this broadcast. Second, I'll do it. Yes. Today, everyone and everywhere connects with a study system. Oh boy. Great. Yeah, yeah, everything works fine. So it's time to appear. Yeah. Oh, something is maybe this way is better. No, not my students. Yeah. Yeah. 1 second. I will draw a lot here, and hopefully I will be able to show something. Yeah. there's money. I need to start talking and drawing. First, let me speak about the curves. Officially, it's called protection of power system. In reality, there will be a two part. The first one, or the science, usually is divided into two parts. The first one is called relay protection. That's what we will deal now. And second one is system automation. It's, to say, higher level. But we will start with relay protection. What is protection and what is a relay? What it's talking about? What is relay protection of power system? First, I should start with idea of relay. What is relay? This is actually a French word, and its original meaning is a special place, special station, where kind of official can swap horse. It's a place where horses are waiting for a legitimate traveler. Traveler who say, has sufficient rank to use state horse. Okay? And to say, giving his old horse and a new one. What's a relay idea here in our business? I have an example. Maybe I can show it. You see example. 1 second. I will get it closer. Oh. Here is my example. Yeah. Here it is. Here is my example. Variable resistance, ground 150 volts. Vacuum valve, wood with a coil, and pair of contacts. It will be 24, and here will be my valve, means 24. What's this one? It's called cesium photo sensor or photo element. Come on. Here I have a larger version. This nice silver coating contains of cesium, zinc and something more, and in the center you can see the disc. It's an anode, cathode, anode. Here should be connection. If photon, white particle, hits cesium cathode, it emits electron, which can be attracted by positively charged cathode. This means what current in the circuit is depend on light efficiency flowing to cathode. This meaning of light efficiency, what it means? What voltage of this point is a function of light intensity. And for triodes, I can draw a nice chart. It's anode current. If I put a current sensor, current meter here, it will be this current as a function of grid voltage. If grid is charged positively, here hot cathode heated can emit electrons. Electrons fly in vacuum space. If grid is charged negative, it pushes electrons back. It's charged positive, it's accelerated. Current in this circuit is dependent or is a function of grid potential. Something like this. Anode current is a function of grid voltage. So at some current, magnetic current to coil will be sufficient to close this contact. Let's try. Let's try to activate. Yeah, can we? Yeah, can we? Maybe. Bit brighter. Bit brighter. Please, 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 please. Please, please. I'm started to ruin my workplace. What we got? What we got? I need to switch this on. This is on. Oh, oh. Here is my light source. My light source. Let's see what happens. Let's see what happens. You see? You see? Light. This thing light is a light relay. What changed this? What changed this? Intensity of light necessary to trigger relay. Here, what? Take a look. What I have at the input. Analog relay, light intensity. What I have, what's at the output? If this is, let's say, X of some black box, I have input and output. What's the input? Analog relay. For my light intensity relay, it's a light informed through diaphragm. What's an output? Output is binary value, closed or open, 1 or 0. So at the first look, we have a box with the input as analog value and Y is a binary value, 1 or 0. Only output possible. Relay function for my case looks like this. At the first, 1. What's this? Threshold. It's a threshold, it's a 3 point. When relay gives an 1 at the output, when it trips, in English it's called trip. So threshold at which relay switched to 1, in Latvian it's nostrāde. Trip in Latvian is nostrāde. So I can call this value x nostrāde. Or in English it's a 3 threshold. Moment or amplitude here, it should be correct, when relay switched from 0 to 1. I would like to show one moment. 1 second, I will switch my relay back. Watch it closely. Wait one more. No 3. Do you saw it? There is one interesting moment with this relay. The trip point is not equal to release. The trip light intensity is not equal to release when relay returns to its previous state. The road is different. Here, let's say red one is when I increase value. I increase. Up here is the trip point. Or in Latvian it will be nostrāde. This one is a trip point. And then I decrease. I go down, up, return to its previous state. R release, or if red is x nostrāde, blue one is x atgriešana or return. Return, release, atgriešana. Atgriešana in Latvian, return or release in English. Value when my relay comes back. Maybe take one. Look what I have. Old, it's a kind of telegraph relay. Here I have coil. if current flows, it has two group of contacts. One is make, normally open, you see this large couple contact. And also here the small one, hope you can see them. This tiny one, service contact, normally closed, they open. One moment, I will assemble a network. This one goes for normal open. I can release this one. Release. Hey, come on. One second. I need a meter. This will be my current meter. I will use this variable transformer and 24 volts power source. This makes me inhuman. I will assemble my circuit. Measure amperes. This goes here. Oh, coil should be connected here. This is not important, I hope. Let's check. Oh. I have my setup, 1 second. to be milliamps. At
At
this
this
moment,
moment,
it's
300
300
microamps, I will increase current. What will happen?
2
2
milliamps,
milliamps,
3,
3,
4,
4,
9,
9,
10,
10,
15,
15, 16,
27
27
milliamps.
milliamps.
Was
Growing.
Yes, 46 milliamps.
Release 40. 45. 40.
You
You
see?
see?
Trip
Trip
current
current
is
is
not
not equal to release current.
This
This
difference
difference
X is called Archimedes coefficient in Wayland or 5 factor of hysteresis. For Lewis is natural to have this difference or hysteresis. Hysteresis factor or in Wayland it will be Archimedes coefficient factor of hysteresis. Usually release value
or return value
is
less
less
than
than 3.
3.
For modern digital relay, this difference is programmable and about 4-5%. For old mechanical relays, natural good or current relay is usable if this value is 0.83. Not less than 0.83.
I can take another.
This one is very good.
Take one second. I see my hand and place my relay. Oh, yeah.
will get you. Let's see. 16, 20, 45, 54, 60, 74. Release 50, 78, 50, 73, 3, 72, release 54. Here's the difference. So it's natural for relays to have this difference between trip and release. Let me draw a chart. Input value, output V increase, input value of X mustard or trip value. We go up, 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 hop. I can draw a chart in time. Let's say what I'm increasing X. What will be reaction of Y? 0, 0, 0. And at moment I need to draw it. It's a trip value. X nostad. What happens with Y? It goes up. Trip moment. Actually, for relay we can, if we look closer, we will see two moments. Moments when maybe moment when relay started to do its job, and moment when output value changes. So here somewhere should be also start moment. Start moment when relay internal mechanics started to move. Trip moment when value changes to 1. And what else? If I go back, I'm going back. X going down. Somewhere is X. Hard question. Or release value. At this moment, Y goes down, relay returns to its previous state. Return, release is moment when output changes to 0, return when relay mechanics on its initial state. Now, I need another object. For short time, I will assemble a very simple network. Network like I have source, I have power switch, and load. One moment, I'll do small assembly work. Relay and come on, let me show you. Relay. One thing I made myself. It's called current balance. It has coil. This balance with steel rods. So when current flows through coil, this rod is attracted. So current force try to swing this balance this way. Here I have a small magnet. I can move it. This magnet attracts this ball up. So actual state of the balance is dependent on what? Of two forces. Attraction from current with coil and return force. It's attractive force of this magnet. By positioning of magnet, I can set what? Trip current. One moment. I'll try to assemble something. And first I need to free some space. I need flags. I need space. Yes. This circuit simulates a power switch. Well, circuit breaker, relay will be my circuit breaker. I need to one moment, I will minus to minus, plus to plus, clicks something work. Next, yeah. It's my circuit breaker. And what about the load? This pair will be my load, motor, and this beacon line. And of course I need a current meter here. Is my meter. Meter. I'm connecting everything in the right sequence. Moment. Connect in right sequence. No. Hey boss. Ja. Just tekēdi veidojam. Ko ir vajadzēja? I don't know what will be the result. It should be something. because I need do a schematic guy, but okay, power off. Smooth. Okay, it's set to 0. One more. One more piece in the puzzle. One more piece in the puzzle. It's a piece in the puzzle is a trip circuit. Was a trip circuit. Okay. Oh. Okay, can you see it? Here on the yeah. I hope you can see them. Here. Current balance, pair of contacts. when balance shifts, contacts are closed, and this triggers release of the switch. Let's try. Here's my load. What happens? Nothing happens. Oops. This way better. One more. Oh, see what happens? Looks like I made a mistake. This way. Yeah. Now you can see load. Look what happens. Do you see it? I have two levers at this point. Trip lever set by this magnet to low, and what else? Load current. Can you see my mistake? I made a mistake. Do you see where my mistake is? Do you see where my mistake is? I've set trip current to low. Trip current to low. My relay, it's a protect. See, I've created a very simple schematic of protection. I have the simple relay with the function current. It receives. It receives current and produces switch release signal. Switch release signal. This pair of contacts is an release and current through the coil. For my relay, you see?
For my relay, you see? What happens? If I
reduce load,
reduce load,
we can live with this.
we can live with this.
But my relay strip on the full
But my
load.
relay strip on the
This
full
is my
load.
first mistake.
This is my
I
first
said-
mistake. I said
Trip current
trip current below
the maximum load current.
the maximum load current.
So E. In Latvia it will be
E.
Nostrada.
In Latvia it will be Nostrada.
E. E towards maximum.
Towards
Towards is a load.
maximum.
So
Towards is a load.
trip
E.
current should be
Trip current should be
greater than
greater than
load.
E load.
Or will happen what you see.
Or will happen what you
At the
see.
moment I
At
switch
the moment
load,
I switch load,
relay trips,
relay
And-
trips, and
my benefits
my benefits
go. See?
are gone.
Magnet
See?
came closer.
Magnet came closer.
I got increased trip current.
I
and
got increased trip current and
everything fine.
everything
Is it
fine. Is it fine?
Let's
Let's
do something.
do something neat.
Where is my fault switch?
Where is my fault switch?
No compromise here. This will
No
be my
compromise here.
switch
Will
of
be my
fault.
switch of fault.
Current falls. Load active.
Current flows.
Load
Load active.
Bad news
Load
happened.
active. Bad news happened.
Oops.
Oops.
Walked.
Walked.
You saw it?
You saw it?
Load active current flow.
Load active.
Bad day
Current
come.
flow. Bad day come.
Where am I?
Where am I?
1 second. Fault.
Fault.
Up.
Up.
Good protection. Good relay.
Good protection.
I have
Good relay.
created what?
I have
Over
created what?
current protection.
Over current protection.
If load current flows, customers are happy. Fault.
Fault.
Triggered. Overcurrent relay send.
Triggered. Over current relay
Signal
send.
and network was released.
Signal
So
and
relay protection
network was released. So relay protection
it
was
isolated faulted circuit.
it isolated faulted circuit.
Show
I would like to show
one more.
one more.
What I done? I have increased the trip.
What I
current.
done? I have increased the trip current.
What works?
What
trip?
works?
Useless
No trip.
protection. Useless protection. Not a good protection. Not a good protection. Will cost me. This will cost me a benefit. A benefit. Good protection. Worked. Good protection. Worked. Good protection. Released fault current. Good protection. Released fault current. Faulty circuit. Bad protection. Trip current is too high. Bad protection. Trip current is too high. Bad protection. Trip current is too low. Bad protection. Trip current is too low. It disconnected here, the load. I'm able here to define key covenants for my protection. First, I'll draw time circuit, say line, customer, line, and maybe more customer. Very simple circuit. A, B, C, and D. First idea, I need to point. What is an area of protection? What protections do protect? So I have some box receiving current and producing trip current. Let's say it will be OCP over current protection. Or in Latvian MSA, maksimāla strāva aizsardzība. Aizsardzība means protection, strāva current, maximal means max. So it's a device what treats if E current at the input is higher than the E nostrā. When the trip current or set point current is above a protection set point. When my device A, sitting in substation A, should trip. If fault here, yeah, if here, yeah, if here, yeah. And if here, no. It's a protected area by device B. Here starts protected area. So for this is for device A. This is for device B. First moment I need to get from my protection. It's called sensitivity. My protected device should be able or should sense any trip in any fault in protected area. So here, 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 all this area should be protected. So my device should be able to operate on any fault within protected area. That's number one. It should have sensitivity. It should sense any fault in protected area. But there is another question. External. So any fault within the red cloud, within protected area, is internal. Internal fault is a fault inside protected area. Sensitivity means what device should trip on any fault within protected area. Fault outside of protected area is external. If here is a fault and my device trips, I will lose this customer, I will pay. My bonds are in danger. This means my device should be able to recognize external faults, or what should fulfill selectivity criteria. Ability to trip on internal fault is sensitive. Ability to not trip falsely on external fault is selectivity. Trip on load, what wrong setup of my relay show, is also non-selective operation. It's not good. So your protective device should be sensitive and selective. That's two. Two more criteria. It should be reliable. Power system operates 24/7. Your device should be able to operate safely. That means very high let's say, mark on reliability. This will lead you to necessity to use very reliable components, very reliable designs targeted to reliability. And one more, protection. Let's say, if protection is a kind of industry or science, it's very conservative. Technique used should be tested, and tested very meticulously. It drives you to very conservative approach. And what else? Oh, and one more. And this one more, is economy. Reliability drives you to the, let's say, high level of redundancy. But technique or technical decisions you take should somehow correspond to the damage, potential damage of fault. For high-end equipment we protect, when the losses are high, also high-end solutions are okay. But economy is a hard thing. You cannot. You should always understand cost of damage caused by not protecting. Finally, everything will end at how to say, a countess desk. yeah. So our basics: sensitivity, ability to sense internal faults; selectivity, ability to not to trip falsely on external faults; reliability, this means being ready to operate, to protect with high level of reliability within prolonged period of time; and economic, let's say, adequacy. That's what we start with. And what else? We should keep in mind what? Idea of start, moment when our device starts to trip, moment when the disconnection signal is sent, release, relay comes back, and return to initial state. Maybe I'll show you one thing. Forget. Let's say. Okay. What is power? Current falls. Oops. What? Once more. See what happens. There is some delay, some time to needed for relay to operate. If I clear fault before, see? Relay returns to its initial state. Inactive word. If I clear fault before protection trip, it returns to its initial state. Tripped. But I can, if I clear fault before protection trip, it returns to initial state. This should. This also may be useful. So appears what I used all my time for today. Okay, we'll continue next week. See. Get ready. Will be many drawings.